Hi, welcome to our lesson on identifying quadratic functions and determining how those quadratic functions look. We're going to look at how the parabola is formed and how a graph of a quadratic has a certain domain and range. So specific vocabulary are quadratic function, parabola, vertex, minimum, and maximum. I'm going to go to the next page and there's going to be a do now. I'm going to have you stop and please look at these questions, stop the video, and solve number 1 and 2. For number 1, you're going to have two answers because you're going to substitute 4 for x and -3. And in number 2, you're going to generate a set of ordered pairs for the given function y equals x squared plus 2 with these 5 domain values. So again, this is a discrete domain. -2, -1, 0, 1, and 2. Pause for a moment and we'll come back with the answers. Okay, now that you have your answer, let's check. When x is -4, you get 36, and when it's -3, you have -6. The ordered pairs for the function with the given domain look like this. 6, 3, 2, 3, 6. If you notice, because the negative and positive x values are both squared, you end up with the same value for y for both -2 and 2. And that's going to come in handy when we're working with our quadratics today. The function y equals x squared is what we have on the graph, and we've done this a couple of times before. It does not recreate a line, and as we've studied before when we were looking at polynomials, because the x value is squared, that's what makes it a quadratic. It's because the degree of the x term is 2. It's any function, and it can be written in a standard form of y equals ax squared plus bx plus c. The a, b, and c represent a numeric value, so either a coefficient of x and a constant. A, b, and c are real numbers. A cannot be 0 because x squared is necessary for the term to be a quadratic. B and c can both be 0, and that's what you see on the graph below, where y equals x squared, and the coefficient of x squared is actually 1. So y equals 1x squared in this case. Before, we've identified linear functions by looking at the constant change in x and how it corresponded to a constant change in y. And those were called the first differences. And it looked a little bit like this. We checked that the constant change in the x values, and then we looked at y. And right now we can tell, well, this is not a linear function. But let's look at what happens, because it's y squared, if we look at the second differences. The second differences in this case are constant. We have a constant change in the x values and a constant change in the second differences. And that's true for all quadratic functions. Y equals x squared doesn't have a constant first difference. Because it's a squared, it has a constant second difference. So let's check and see if we can determine whether or not a set of ordered pairs is a quadratic. So the first thing we do is always check the first differences. Yep, those are all +1. Now let's look at the change in y. If I look at the change in y, -9 to -2, I've got a change of 7, but then if you notice, it's only a change of 1, a change of 1, and then a change of 7. But that's just the first difference. Let's check the second difference. The second difference is -6, 0, 6. Well, that's not constant, so this is not a quadratic. The second differences are not constant. We always want to double check that we have a constant change in the x values, because if there's no constant change in the x, don't even bother checking the y. It's not going to be a quadratic. Another way to tell whether or not a quadratic is a quadratic function is to look at the standard form of the equation. Y equals 7x plus 3. Well, that looks really familiar to y equals mx plus b, and that wasn't a quadratic function. Ax squared is what's needed to make a quadratic function. We have a linear function. There is no x squared term. If we look at this one, although it's written as y minus x 10x squared equals 9. If I solve for y, I'm going to see that y equals 10x squared plus 9. And I see that I have an a term of 10x squared, and I have a c term of 9. And it's okay if I have no b term. It's still a quadratic function. I have a binomial, 10x squared plus 9. The largest degree term is 2, so that makes it a quadratic. A quadratic function, only the a cannot equal 0. It's okay for b and c to be 0. So let's look again to see if a set of ordered pairs is a quadratic function. Well, the differences are 1. I check my first differences, and then I check my second differences. Let's check by looking at an equation. Well, is this a function that is a quadratic? I'm going to solve for y. I'm going to check to see if I have an ax squared term, and I do. So yeah, this is a quadratic function. So to recap, to identify whether a function is quadratic, it has to be written in the standard form ax squared plus bx plus c, or if you're checking from a table, you need to have a constant change in x comparing to a constant change in the second differences of y.